So a little quick bit about the Energy Center and the buildings team, of which Scott and I are both a part. I think our main focus here is energy efficiency, and that's everything we do is related to energy efficiency. And we do that primarily 3 different ways: through education and training, professional development like this webinar here, through research, and through technical assistance. And our specialty is commercial new construction projects. Some examples of the technical assistance that we provide are energy modeling and daylighting, 2 of our top 2 deliverables on this slide. Scott and I do a lot of that. So,
yeah, definitely. I guess to kind of kick off the daylighting presentation itself, it's good to get a little perspective about why lighting and daylighting is important. And I think we all know that there's a lot of talk in the world today about energy crisis, global warming, greenhouse gases, and it turns out that lighting energy is a very large portion of the overall U.S. domestic energy usage. It accounts for about 8% of our overall energy usage, and that's roughly 315 terawatt hours annually, and that's only expected to grow, approximately increasing 50% by the year 2025. What you see on the slide right now is a bar chart of an energy model that I created. It's of a kind of a typical prototype standard office building in Madison, Wisconsin. I think it's like 50,000 square feet. And of that building, annually, the electric consumption can be broken down into what turns out to be 5 categories. Fans is in gray, pumps is a very small blue slice, a lighter blue slice is cooling, miscellaneous equipment, and then lighting, which actually makes up the majority of the electrical consumption of a standard office building throughout the year. The bar on the far left shows the baseline, so they put a lot of code values for things like lighting power density and equipment efficiencies. And you can see that lighting actually accounts for about 50% of the overall electrical energy usage of a typical office building. And then if we want to decrease the energy of our building, one thing we can do is apply more efficient lighting. And the second bar chart shows what would happen to the energy usage of that same building annually if the lighting power density was dropped from, I think, code value of 1.0 watts a square foot to an efficient lighting layout of about 0.8 watts a square foot. So the lighting drops about 20% or so. But then you can go even further and control that lighting, shutting off when it's not necessary. And put occupancy sensors and things like daylight harvesting, which we're going to be talking a lot about today, into your building. Then you can drop the electrical usage of the lighting system another 20 or 22%. And so you can see pretty big decreases in your overall energy usage. And when you scale it up to all the buildings across the U.S., you can make a pretty sizable amount of our domestic energy usage. Saving energy is one great thing about daylighting. However, there's other useful attributes as well. This slide kind of illustrates 2 office settings. One, there's kind of a darker cube farm-like environment with more cave-like feel to it. There's not a lot of natural light, and you definitely don't have a connection to the outdoors. But in the right, the right picture, you see a very open and well-lit, kind of day-lit ambient working environment, and daylighting a space just makes it a more pleasant place to be. Studies have shown, and there's links available for these, that workers who work in a well daylit environment see increases in their productivity, job satisfaction, as well as students that study in classrooms that are daylit have been shown to show increases in their learning, and retail sales even increase in daylit shops.
A bunch of those studies are on our Daylight and Collaborative website, as well as the links at the end of this presentation as well. So.
Yeah, definitely. To a lot of people, and particularly building owners, the decision to go with daylighting or not really comes down to money. They want to know what the payback is of installing a costly daylight system. However, other opportunities exist with respect to incorporating daylighting into a design, and those are lowering the environmental impact, just how much impact on the natural environment a building has, as well as just creating a very pleasant and productive space to work. Now, it's not as quantitative as showing hard energy savings. However, since salaries, health benefits are such a large portion of any building owner's costs, then seeing just a very small incremental rise in worker productivity or a decrease in their health benefits can have a big impact on a building owner's bottom line. So, plus, since we spend about 80% of our life indoors, it's important that we enjoy the time that we have inside. So, with that, I think Tate's going to talk a little bit more about what daylighting actually is.
Yeah, well, I think you're right, and daylighting, at least a really good daylight plan, is going to deliver all three parts of that triple bottom line: the economic part, the human or societal or cultural impact is greatly affected, and the environment as well. So if you do it right, you should expect all of those three things. It's important to understand that daylighting, there's no standardized definition out there. It means different things to different people. But for us here at the Energy Center, it's really important that daylighting saves energy. I think that's one of the greatest potentials. And if you do it right, you should be able to expect that. In addition, you're using natural diffuse light in the space, and you're rejecting direct sunlight, which brings heat concerns and glare. And then finally, you're really engaging that view and that connection to the outdoors with your designs. So if you can do all those three things, I think you've got a really successful daylighting concept. So when you're working through these ideas, it's establishing the performance targets and developing the daylighting concept. That's what we're going to be focusing most on in this presentation. We have another presentation next week, and that's going to be on deciding how to analyze your plan. There are three ways to analyze it. You can either do a simulation, which could be on the computer, it could be a physical model, or you could do sort of prescriptive requirements. There are a lot of calculations out there to help you get in the right ballpark. Either way, it's more of a predictive design tool, and then usually follow it up with some type of measurement in the post-occupancy phase. Taking all these things together and rolling them up into your plan will help you improve it over time. So the first step is setting performance targets. Energy savings targets, like we said, are particularly near and dear to our hearts. There are a lot of ways you can do that. Certainly percentage above code is the big way. We see LEED, USGBC's rating system, focus on that. We'd like to break it down a little further. What are the therm implications? Scott mentioned the huge electricity potential, the savings in that category.
Also peak savings as well.
Yeah, especially peak. And, there are a lot of reasons peak is important. Specifically, engineers design their systems to handle peak loads. So by shaving your peak load, you don't need as much equipment to handle that load. And that's a first cost savings, not an operational cost savings the owner's going to see later. Additionally, peak loads. We have enough load in the grid to handle everybody's needs except at peak times. So when we talk about building new power plants, then we have to build new ones to handle that peak demand. It's kind of like traffic. It's usually fine except for peak times during the morning and the evening when people are commuting. So reducing that peak load has a huge societal benefit. But finally, I would say that ratchet charge So an owner sets, a peak condition, and that is charged against him or her all year long, and until they
The newest
ratchet
new
up.
one set.
Right. And that, dovetails right into cost savings. Reducing those peak loads is going to have a huge impact on saving operational costs for the owner. So that's a big motivator. In terms of daylight, we're measuring that with usable foot candles in some cases, view and glare, which are a little more qualitative than quantitative, but in a balanced daylighting scheme, those are just as important. Delivering a high quality of light as well as enough light is really important. And then finally, thermal comfort. There's a lot of heat gain and heat loss, and how you're tracking that in the energy model, and balancing that with how much energy you're saving, and what kind of quality light you're getting is part of the performance targets that you want to set at the beginning of this process.
It's good to definitely have aggressive targets with respect to energy savings and cost, but you don't want to set them so high that they come at the expense of occupant comfort, and that's where really balancing those targets with respect to your glare and your thermal comfort are important.
Definitely.
So definitely consider those.
So, how you go about doing this, there are really only 7 big moves you have in this process, but thousands of little permutations. And I think, the big opportunity here is to adapt your building to the region that you're in, and really have it be part of the culture and the context of the site. Starting, it's a holistic plan, and you want to have each one of these concepts addressed, starting at the macro level with climate, and then winding up at the micro level and what type of glass you select. And, these aren't hard and fast rules. You can certainly have a lot of play within each one, but you can't expect to, make it up by just addressing a few of them or just the glass type and expect to have a good daylighting plan.
Yep. So I guess to kick off the discussion of these daylighting concepts, the first is climate. And it's very important and often missed to first consider, where am I building this building? And what kind of climactic conditions is it going to be experiencing throughout its life? A couple hundred years ago, if you went from one climate condition to another, the buildings that were designed in those spaces were, very different. Whether it's, adobe shelters in the desert that have high thermal mass and a lot of natural ventilation, are going to be very different than, a highly insulated igloo or, wherever. It was very climate dependent building types. But nowadays, you go to any big city, you see a standard skyscraper. They all mostly look the same. And so considering where you are and what you're going to be dealing with is the first step. This is a plot of the U.S. climate zones as broken down by the U.S. Department of Energy. And what it speaks to is there's a lot of different climates just across the U.S., let alone across the world. Mostly it depends on latitude. It's going to be very much warmer in the south as in the north. But there's also degradations with respect to cloud cover, humidity. And we're going to point out 3 kind of alternate climate zones examples. The first is Seattle, Washington in the northwest. The second is Phoenix, Arizona. And the third is where we are today, which is Madison, Wisconsin, which is currently experiencing a beautiful spring day of snow and hail. No, well,
It's not pretty out there.
it's not pretty out there. So to talk a little bit more about the sky conditions in these 3 spaces, the first example, Seattle, is going to be a predominantly cloudy environment. They only get 71, on average, clear days every year, which is about 1 in 5. And the plots at the bottom show, starting in January and ending in December, how the cloud percentage varies over the year. The gray line is cloudy, the blue line is clear. And you can see in January and in December, about 4 and 5 days in Seattle are cloudy. So not a lot of direct sunlight, which isn't necessarily a bad thing. You can still get 2,000 foot candles in a cloudy condition, which is more than enough to daylight by. However, that space, that illumination is maximized at the zenith. In a cloudy sky condition, you get most of your foot candles from, or most of your lumens from the sky's peak. And so you definitely don't want to over glaze your roof and have a very high skylight to floor ratio. That could just cause glare even in a cloudy condition. Alternately, Phoenix, very sunny. 1 and 2 days are sunny there. So glare is a very big concern. You're getting a lot of direct sunlight, and in fact, you're getting the potential for reflections off of the ground. We've heard complaints about daylight systems being overridden because people have to close the blinds when the sun strikes all the cars out in the parking lot. And so really minimizing both reflections and that low-angle sun in the evenings and the mornings in Phoenix is going to be very important. And then Madison, Wisconsin, well, we're somewhere in between. It's cloudy here a lot. It's clear sometimes. It's not one of the extremes. So the daylighting approach that we have in Madison needs to be balanced in order to take into account all the different conditions it'll see.
So looking at this chart really quickly, we see cloudy conditions somewhere around 2,000 foot candles. Sky is delivering. In sunny climates, 7 to 10,000 foot candles. There's a really wide range, and in some climates you have to deal with both. And you typically need 20 to 50 foot candles to read by. So managing how much of that daylight, skylight comes into your building becomes really critical.
Yeah.
It's going to be a different strategy for each condition.
And then to kind of break apart each location in terms of temperature as well, Seattle is going to be the mild climate. The lowest temperature isn't very low, the highest temperature isn't very high, and therefore you're not going to have to design against very extreme peaks in temperature. Phoenix, however, is going to see very high temperatures. On the design day, the cooling design day, you need to be able to offset 108 degrees of Fahrenheit outside.
Yeah, that's where peak load shaving becomes really important.
Because your cooling equipment is going to be working very hard during that time, and if the electric lights are off, it won't have to work quite as hard. Alternately, in Madison, well, we see pretty hot summers, but they're shorter than Phoenix for sure, and our winters are much colder. On the heating design day in Madison, Wisconsin, the heating equipment is going to have to be able to handle an outside temperature of about negative 11 degrees Fahrenheit. So in Madison, maybe it's a good thing to let some of that solar heat into the space and help the heating equipment to not work quite as hard. But once again, it's a balance. You don't want to really open up the exterior with lots of window-to-wall ratios in Madison, because even though you're letting in a lot of outside illumination, you are also going to let out a lot of heat in the winter, and that's going to really up your heating costs. So just kind of summarize a little bit, the climates are varied and they vary throughout the year, so it's a very dynamic condition that we have to design against. And then with respect to building type, there's a lot of different kinds, whether you're talking about an office or a healthcare facility, classroom, or a warehouse. You need to understand that for sure, but also with respect to that, you need to understand a little bit more about how that building uses its daylight. And the first kind of dichotomy of building types that we're going to look at is a skin versus a load-dominant building. Once again, if you go back 200 years, the buildings are going to be a lot different than the current design. And that's because 200 years ago there wasn't cheap available electricity in the quantities that we have today. So building designers used daylight and natural ventilation, and therefore their buildings were very optimized to maximize the perimeter space available for these daylight and natural ventilation. You can see on the left, it's the San Francisco Federal Building, It's a well daylit building. It has a very thin floor plate, and that means high aspect ratios, very rectangular in shape. So it doesn't have a lot of core spaces that don't have access to perimeter glazing on the wall. It's a very tall building. However, a daylit building could be a very short building as well. 1 to 2 floors means you have a lot of roof access in order to get top lighting into your space and decrease the loads in those areas as well. On the right is a load dominant building. And what I mean by that is there's a lot of core spaces with heat gains that don't have access to the outside. The right building is actually the Portland Public Service Building, which is affectionately known as the world's tallest basement. The design of this building was not driven by daylight or occupant comfort. It was driven by style. It's a postmodern building that isn't necessarily the best place to work.
Yeah, those little punched openings create a high contrast ratio between the window and the solid wall, so there's a lot of glare potential there. And I really love the idea that the building can respond to place, and that performance trumps aesthetic, at least in these 2 examples. So, and even that the performance can inform the aesthetic, which I think is even more important.
Yeah. So I guess our mantra in the daylighting world is that a thin building equals a healthy building.
Excellent.
Another consideration to respect to daylighting that needs to be taken into consideration is the ceiling height. Daylight is most effective when it can be brought deep into a space, and high ceiling heights will encourage that because the depth through which daylight can penetrate a space is proportional to the height of the windows. A rule of thumb is that daylight can penetrate about 1.5, maybe 2 times the head height of the window into a space. So the taller your ceilings, the more daylit area you can attain. Similarly, high ceiling heights are great for top lighting. A single skylight can cast its light more diffusely over a bigger area than a low ceiling height room. This is because the area that a skylight can affect with daylight is proportional to the ceiling height as well. A good rule of thumb for that, about 1 times the total ceiling height will be daylit, the radius will be 1 times the ceiling height. So if you have high ceiling heights, the potential for daylight only increases. The last kind of building type difference I wanted to mention today is having open areas versus more private rooms. In an open area, you have the ability to control the lighting scheme a lot more simply by having only a few photosensors in the space, as opposed to private rooms where each space has to have one. And therefore, the complexity and the cost of the daylighting control system will be that much higher. On the left, you see a very open office plan, which is a great design because it has, once again, very high ceiling heights and high window heights, allowing that daylight to come deep into the space. It also has white ceilings and white finishes, light finishes throughout the space, which means that daylight isn't going to be quickly absorbed by the reflectances in the space. It'll be reflected and get even deeper into the space. And then finally, that design is so good because the partitions in the space are low. High partitions will absorb the light and quickly lead to the daylight penetration being cut down substantially.
Oh, you mean like the ones in our office?
Yes, like the ones in our office.
But they're recycled, so it's okay.
Yeah, they have other aspects that are good.
Sometimes you have a big opportunity for orientation, sometimes you don't. If you're working on an existing building, it's definitely already there for you, and your options are somewhat limited. But I think you could see from that last example that it's possible to really tap into that potential. And occasionally a tight urban site can be very constrained. But I encourage you not to throw up your hands. There are a lot of opportunities, and that one SF Federal building is a really good example some advanced daylighting on a tight urban site. So just a few things to keep in mind with orientation. It's really easy to manage direct sun from the south and the north face. But when the sun's low in the sky, in the east and the west, it tends to cause glare and hot spots and intense thermal gains. So what we like to do is maximize that north and the south side. Similarly, the south side of a building can provide 10 times as much light as the north. So your building shouldn't look the same on each side, and we'll kind of get into some options for shading and stuff like that later, which is another opportunity to contextualize your building for the site that you're dealing with and for the region that you're in. This progresses from good to bad to ugly really fast. And you can see in the ugly situation, it's got its long sides facing east and west, and the building's oriented on a north-south axis, and that makes those peak gains really intense. It requires a larger size mechanical system to handle those larger loads, and as an example, I've actually seen a building where they did everything right. They had the right kind of glass, they had the top-of-the-line control system, they had proportioned the glass properly, and the only thing was that the building was pointing in the wrong direction, and they didn't adjust for that, and it defeated the daylighting system. Talking duct tape over the sensors and all sorts of other
Closed blinds.
So it's really important to keep all these ideas in your plan when you're going through the process. And here's kind of like a sun's eye view. It's a really easy way of understanding where the sun is coming from and convey that to the rest of the folks on the team. When the sun rises in the east, it's usually low in the horizon. It's always low in the horizon. And it's got direct penetration into the building, so anything the sun sees, you can see in this BIM elevation here. And there's a lot of glass there, so we have to protect against that in the early mornings. As the sun progresses throughout the day, it raises up into the sky dome, changes color, and we're looking down pretty much on top of this building right now. It's seeing a lot of the skylights that are part of the concept, and so arranging those skylights, putting the right type of glass, and making sure the size of those skylights becomes paramount in the design consideration.
And it's really obvious on the windows on the south side of that building that the projected area has become much smaller and therefore more easily shaded with like an overhang.
Right. It's really tough to shade the windows in the east and west face when the sun is low in the sky and it's moving across the horizon really fast. So here's an example of what the sun sees in the west face. Is that right?
I think you went up.
Yeah, sorry about that. It's seeing a lot of glass there, so providing darker glass, perhaps blinds or some other way of diffusing the light, fins. Just cutting down the amount of glass on that face is going to make a big difference for the building's performance. So just to kind of summarize, in terms of the orientation, the sun is a dynamic element in your design, and you're usually dealing with a static envelope. So what types of risks are you willing to take is going to be a really big question you have to ask, because you're not going to be able to handle all those sun's conditions all the time, but having sort of a
plan to minimize the negative aspects of a dynamic lighting and bring out the great aspects of the sun.
Yeah.
The fact that it changes and really connects us to our natural biorhythms is a great aspect of taking advantage of the orientation.
Definitely. Okay, you ready?
Sure.
All right.
So lighting control. So now you have the right building oriented the right way in the right climate, and your lighting scheme needs to be controlled. Well, how do you control it? The first question is, what do you control it to? What's your performance target? And that usually comes in terms of a foot candle or a target illuminance. This plot shows some illuminance ranges recommended by IESNA for four different building types: warehouses, offices, schools, and retail. On the far left is warehouse. It's broken out into a few different types of warehouse, but overall the range of illuminated foot candles necessary is very low. It could be as low as 5 or 10, or as high as 25, 30, maybe even 50. But you don't need to provide a lot of light to a space that's storing boxes. Alternatively, the allotted foot candles increase when you switch into an office environment. In the 30, 40, 50 foot candle range is often recommended. And note from earlier, 30, 40, or 50 foot candles is very low compared to the amount of illuminance provided by the sun. On a typical sunny day, 7,000 to 10,000 foot candles. On a cloudy day, 2,000 foot candles. That's orders of magnitude greater than what's necessary to work and read by. School grows even more. You can get up into the 100 foot candle range pretty easily, but 50 is still reasonable. And then retail, it's very high. The scale actually goes up to 500 foot candles for retail, and that's because a lot of business owners really want to put a lot of light on those shiny ceramics and jewelry, which isn't always necessary. Sometimes it's more about the contrast of having an adequate amount of light on the merchandise with contrast between it and the background to really pull it out and sell that product. So now that you know what you're shooting for with respect to light levels, you have to control the electric lights to deliver it, and only deliver it when the exterior luminance from the sun isn't high enough. So there's a few different types of controls that you could apply to your electrical lighting system. The first is no control, and I think we're making the point right now that if you have no control on your electric light, you're probably not daylighting the space. That's only really considered a daylighting design if you have very motivated occupants. And some buildings have motivated occupants. Auto Leopold is one example of a space that doesn't have automated photosensor control. However, their lighting savings is much higher than a typical automatic control because its occupants are so motivated to save energy. But that's a very educated and very motivated occupancy. And to be safe, we recommend putting automated controls in. So the first level of automated control is on-off, and that can be seen in the blue line on this plot. Basically, an on-off dimming or switching system will keep the electric lights on until the exterior is supplying enough foot candles to meet your target. So at 50 foot candles, which is the target on this kind of typical office, the electric lights would go off. And then you can start realizing energy savings. However, that step change in electric lights is very abrupt when you're talking about going from 100% power of your electric lights down to 0. And when that step change occurs, the occupants can notice it and complain about it. And those complaints can pretty quickly pile up. So it's maybe the cheapest way of going, but not necessarily the most comfortable way of going. On the other end of the spectrum is a continuous dimming. For continuous dimming, the electric lights are ramped linearly to provide just enough illuminance to offset the remaining portion of the light needed from the exterior that the exterior isn't provided. However, once you reach the target illuminance, the electric lights are off completely and you're saving 100% of your electrical lighting energy. And somewhere in between those two is like a 2 or 3 step dimming approach. In this plot, it's the red the jagged red line, that's the two-stepped. It steps down at 18 foot candles, and then again to 1/3 power at, what is that, like 35 foot candles. And it's not quite as noticeable as the on-off switching. However, there is still a step change. So the most energy can be saved by a continuous, and it'll be the least noticeable to the occupants.
That's correct. It works best in ceilings with lower head heights as well, because it's less noticeable when the foot candle level changes.
And the savings is kind of seen by the shaded areas. If you go from on-off to two-stepped, that whole area of blue will be the electrical energy savings that your lighting system will achieve.
Yeah.
If you go from two-step to continuous, the red shade will be your energy savings.
So there's energy savings, but then there's a first cost component as well, right?
Yeah. The continuous will be more expensive because it's a more complex system.
Mm-hmm.
And the on-off will be the least expensive, but will have the least potential for savings. So they all have different paybacks associated with them.
Mm-hmm.
Another thing to consider with respect to lighting control is zoning. So when you lay out your lighting design, it's important to know where the daylight is going to be. And oftentimes always, it's right next to the windows or under the skylights. In this plot, we go back to that open office plan and talk a little bit about how they zone the electric lights in order to control them effectively. In the plot on the right, the windows are at the bottom of the screen, so that's where the most daylight's going to be. And the depth of that first controlled daylight zone is proportional about 1 or 2 times the overall ceiling height. In this case, it's about 20 feet because they have such high windows that they can get light deep into a space. All the electrical lights that provide light to that space are controlled by a single photosensor, which is a very easy and quick way of controlling a big space. A second daylight zone is actually in the 20 to 40 feet from the exterior glazing range. There's a second photosensor that controls that entire bank of lights. And then the third zone is actually not a daylit zone because now we're far enough away from the exterior glazing that not enough daylight penetrates, and therefore that's just a manual switch. It's really important to commission your daylight control sequence, and I think we'll talk about that briefly in a second, but just wanted to kind of break out the zoning schemes that you should be taking into consideration when you're laying out your lighting plan. We talked a little bit about controls, but maybe we should talk a little bit more about what you're controlling. A lot of times lighting designers talk about the energy associated with their lighting design in terms of lighting power density. This is actually the installed power of the lighting system divided by the building or area square footage. So if you take and you sum up all the fixtures in your space, how much power they'll consume at peak, and then divide that by the space area, you'll get a lighting power density. There's a couple ways to calculate it. The easiest is the whole building approach. It's very fast and easy and more stringent. However, a more time-consuming way, but a way that gives you more latitude, is to do the lighting power density space by space. If you switch and talk about just like the whole building method, then codes, in this case ASHRAE 90.1, which references IECC, specifies a baseline or a maximum lighting power density that these 4 building types can actually have. Warehouse is the lowest at 0.8. Offices are allowed a little more lighting power at 1.0 watt a square foot. Classrooms step up to 1.2, and then retail is highest at 1.5.
So setting a good target for your lighting design early on is a good way to save money at very little cost. And there's some great references out there, the Advanced Energy Design Guides that speak specifically to these project types, Advanced Buildings Core Performance Guide, and then personal experience being the best of all three. So to know what you can deliver in terms of foot candles for the minimum amount of watts available is a pretty powerful way to just reduce your energy use.
Yep. referencing back to that first slide we presented, if you were able to decrease the 1 watt a square foot required by code to 0.8, then you can cut off a large percentage of your electrical consumption.
Yeah. Do this first, then daylight.
It's a good way of putting it. So to kind of break down the control section in general, there's kind of a lower cost but lower potential for savings approach, and there's a higher cost but higher potential for savings approach. The step dimming isn't going to be as costly to implement. However, it won't garner as much savings as the continuous dimming will. You'll also have a trade-off there in occupant comfort. Open loop versus closed loop. An open loop being, there's one or just a couple photosensors that are measuring the exterior luminance level and then making some assumptions in their algorithms to control the interior electric lighting. Not as costly, simple, but more simple to employ than a closed loop where there's a lot of photosensors throughout the spaces and they're measuring directly the illuminance in the space and controlling the electric lights accordingly. Simple zoning versus aggressive zoning. Our example had multiple daylit zones with different photosensors controlling them. You could have just one. You could have one large one, or you could have many small ones. The more you have, the more optimum the photosensor control will be, but the more costly the system. And then finally, the difference between having kind of a code level of lighting power density, just doing what is required, versus going a little further and putting in a more efficient lighting system. And then finally, the point we like to make is that even though control systems are designed and marketed to work out of the box, it's really important to commission the system, often by a third-party commissioner, to really ensure that that level of accuracy in which your control system is operating as designed.
The more complex the system, the more parts that it controls, the more important it is to commission it.
You'd hate to design this great system that just isn't working like you designed. And then I wanted to mention before we moved on to glazing area that code is not just requiring lower and lower lighting power densities, but in the future it will require more and more sophisticated controls. In the past, it's required that in daylit areas, which are just areas adjacent to windows or skylights, you have at least a separate circuit, and so they're controlled with a switch. However, pretty soon, 90.1 2010, you'll be required to put photosensors, automatic photosensor control on these areas. So the earlier you can get good at designing these systems, the better off you'll be in the long run.
So moving right along to glazing area, how much glazing you use. I think engineers are always telling us architects to use less glass.
Why do you need that much glass?
But really, what you need to look at the whole picture and the concept and all these parts and how they come together. That's how you can come to a good agreement about what's a reasonable glass area. There are trade-offs along this process, and having the engineer at the table, and understanding all of those concepts and how they work together is
just makes us feel better.
Yeah, it's
more important.
It's the basis of integrated design. Really, good daylighting is a metaphor for integrated design. So
it's true. You got to bring everybody together to do a good daylighting design, from the architect to the engineer, electrical engineer, lighting designer, interior designer even can affect the daylighting design.
Huge impacts. So let's not forget the owner. They need to be on board with that.
Who? That's right.
And the contractor, certainly, as well. Everybody has it. Not to mention the energy modeler.
Those guys are great.
It's true. So from a code perspective, from a prescriptive approach, ASHRAE recommends less than 40% window-to-wall ratio on the window side, the glazing side, and less than 5% skylight-to-floor ratio for the skylights. Now, certainly there are ranges. You can exceed these, but you have to leave the prescriptive approach and do a performance-based approach, and that's where energy modeling, daylighting modeling comes in. Interestingly enough, the highest performing buildings that we see kind of run around 20 to 30% window to wall ratio, and the higher you get, the more daylight availability you have, but the more heat loss, heat gain issues you have, and certainly more potential for glare and all those other issues. On the right here, you see these prismatic skylights. They're great. They're translucent, and they're specially shaped to diffuse the light that comes in. So even though it's a very small area, you get an amazing quality of light in that space. In terms of the window wall area, there's this balance between daylight availability and heat loss through the envelope. And finding that sweet spot is going to be different for every building type. Certainly going to be different for retail than it is for office. Different concept. Yeah.
Yeah, those are just the assumptions I used to create the plot in the former. I used Spot. It's a free tool that anybody can quickly pick up and do some pretty quick analysis on a given space.
Mm-hmm.
These are just the assumptions I used to create the plot previously.
Okay. And then a similar plot for skylight area.
Yep.
And there's even a greater difference between that and windows. So keeping that skylight area below 10% and ideally below 5 for most spaces is going to work well for you. Again, the Advanced Energy Design Guides give some good prescriptive calculations, but if you really want to know how those things affect your space in terms of energy use, you have to do an energy model, and it helps to do it early in the process.
Yeah. Those numbers were generated with SkyCalc, which is another free tool, simple to use, and easily picked up.
Right.
The links for both of those are provided in the link section of the webinar,
Mm-hmm.
and I think we're going to go into more detail on both of those in the second webinar, so stay tuned.
Sounds good.
Shading condition. So now we're talking a little bit more about the exterior of the building again, and what kind of shading devices you can use to cut down on the potential for things like glare and solar heat gain. This is back to that same picture of the San Francisco Federal Building. The facade, the orientation of that building was constrained by its urban location, and so they had a big west-facing facade. So what they do, well, they didn't just throw their hands up in the air and call it a day. They put a very thoughtful set of exterior fins, which are great for shielding that big west facade from the low angle, late in the day western sun. And I think we're going to go in a little bit more with respect to the. Yeah, do you want to add something?
I do. Yeah, there's that big overhang at the top of the facility as well, and that's influenced by higher angle sun and cutting down that. But I think what's most important to realize about the physical shading devices is that they are probably the most susceptible of any element in these concepts to value engineering. Folks look at that elevation and they immediately see what they can tear off. But if these are well integrated into the daylighting plan and the energy savings that you put at the beginning of this process, it's harder to take them out. And I would say when you do energy modeling, at least what we found is that these physical shading devices don't have a huge impact on standard building types. But we don't see like huge amounts of energy. And so it makes it really tough to keep them in there from a cost perspective. What they do provide, though, is a great quality of light in the space, which is harder to quantify. Yeah. And additionally, if your targets are super hardcore, like if you're going for a net zero building, you cannot do it without physical shading on the exterior.
Every little point counts. Then.
Yeah, those economics just turn over 180 degrees.
Yeah.
So. Thanks.
Yeah, thank you. To get a little bit more into overhangs as opposed to fins. For any shading device, you need to know where the sun is, and the sun's position, like we mentioned before, is going to change, not only throughout the time of day, but also throughout the year. We express the sun's position in terms of the altitude and azimuth. The altitude is going to be the angle off of horizontal that the sun is making at a given time. It goes from 0 when it's at the horizon to 90 degrees when it's straight up at the zenith. The azimuth is the angle at which the sun is off of north. So on the fall solstice, the fall equinox, when the sun rises in the east, it'll be at 0 degrees azimuth. And then as it continues throughout the day, it'll go from 0 all the way over to 180 and set in the west. So those are the two kind of free parameters to express the sun's position as a function of time. And then if you want to know, well, is my overhang going to shade, or alternatively, will my fin shade my west facade? Then you need to have an overhang whose depth is great enough such that the angle that it makes, the farthest extent of that makes, with respect to the lowest part of your glazing, that angle needs to be greater than the altitude of the sun at a given time. It's a little hard to see. Hopefully, if you print off the PDF, you'll be able to see where in this plot the altitude is. Alternatively, it's great to have a depth of overhang out from that south facade, but you also need to have an offset of the overhang away from your window, such that as the sun passes into the west or is still in the east of the sky, that extra dimension out from the width of the window can shade for extra periods of time. And the angle that extra width needs to make with respect to the extent of your window needs to be greater than less than the azimuth at that given time. So what you're saying, the sun has all kinds of azimuths and altitudes. How do I know when the shade is going to be shading my window? You need to establish a shade date. In terms of what a shade date is, it's basically the latest time of the year that the sun is going to not penetrate the glazing directly. I've picked July 31st. It's a pretty early shade date, but it still encapsulates the hottest days of the year for us, when the sun entering the space directly and bringing all that solar heat is going to be a negative impact for our cooling system, which is already taxed by the hot temperatures outside. So there's a link to a website called the Sun Position Calculator, and if you go to that website, you can, for many major cities throughout the U.S., for a given date and time of day, you can calculate. It'll give you what the sun's altitude and azimuth is at that time. For July, a very hot day of the year for us, July 31st at 2 o'clock p.m., the sun's 62 degrees up in the sky and 209 degrees off of north, so 29 degrees into the west from the south. Once you have those kind of critical altitude and azimuth numbers, you can use some pretty straightforward geometry to calculate what the depth of that overhang needs to be, as well as what its offset needs to be to shade a window at that time. For our overhang height, which is 6 feet above the lowest part of the glazing, the overhang needs to be 3.2 feet deep and offset 1.8 feet from the window in order to provide shading, complete shading of the window at that time. And so I put together 3 really quick AGI 32 models, which just show the level of sunlight penetration of the space and the overhang that I just described for 3 different times of the year. The first, in the top left, it's July 31st at 2 o'clock p.m. in Madison, Wisconsin, which gives you the latitude. The overhang is adequate. You see no direct sunlight and therefore no added heat gain that the cooling equipment has to offset. If you wait just 3 hours as the sun starts to dip in the sky and get lower, then you start to see a little sliver of direct light penetrating the space. And alternatively, if you go a few weeks later in the year when the sun is not as high in the sky at 2 o'clock p.m., but is dipped lower in the sky as it approaches its minimum during the winter solstice, you're starting to get even more direct sunlight penetration. And August 21st, it's still going to be hot here, especially at 2 o'clock p.m. in the afternoon, but because we've designed our overhang to provide no shading in July 31st, and we're not seeing a lot of direct solar penetration at that point. However, if we hadn't put as big of an overhang, you'd see more and more, which causes more heat gain, more cooling equipment work, and more potential for both glare and thermal discomfort.
Yeah, thanks.
Sure. And glass type.
Yeah, so now we're at the bottom of the list, and glass is probably the most energy-intensive of all the scheme components, both in its manufacture but impact on energy use for the building. And I think what's most important to keep in mind is the balance between the aesthetics of the glass, and what it portrays about the concept of the building, and the performance of the glass. So qualities like reflectivity or tint and opacity are going to play a large part of how this building works in its context. So for this first slide, just looking at a standard IGU insulated glazing unit, it's a standard unit is 2 1/4-inch panes of glass sandwiched between a spacer, right, and an aluminum frame. And you see this all the time in commercial construction. It's very typical for its cost, durability, and its weight. It's pretty optimized solution. But what you need to do is look at the entire assembly, not just the center of glass values, but what type of frame you're using when you're calculating the U factor of the unit. And when we're looking at the glass and looking at the potential for losing heat out of the envelope, this is a typical Madison condition here where we have a heat loss, 0 degrees outside, 70 degrees inside, and the way it loses heat is through conduction, through the materials, through the glass, through the frame and the spacer, especially. And ways we might mitigate against that is to make the glass thicker, to add another pane of glass, so a triple pane unit, or add like a super insulated, gas fill argon or an aerogel in that cavity. So secondly, through convection, basically hot air in the room hits that cold surface of the glass and moves the air in a convective pattern.
Or the wind is roaring outside on a cold winter night.
That's right.
And that forced convection on the exterior.
Yeah, it drops that interior temperature and can create uncomfortable air currents at the window wall. Yeah. So that's especially a problem when you have large, expansive glass. Smaller areas are not so much a problem, but that convection is happening between the panes of glass as well, and putting in an argon fill actually slows that process of convection and increases the R value of the glass.
Why don't you tell me that thickness is optimized or something to prevent?
Yeah. So in terms of the placement, that 1-inch glass, you could spread those pieces of glass further apart, but in that case, it would reduce the convection, but it would it would reduce the conduction between the panes, but it would increase the convection between the panes. So that's sort of the optimal distance of the panes.
That's right.
And then finally, every body emits radiation, and glass is no exception. Thanks. So a standard piece of glass would, a clear piece of glass would emit like, I don't know, 0.84 is emissivity rating. And then if you had a nice low E coating in there, it would drop that exponentially down to like almost 0.2. So reducing the radiation from that glass is potential.
I was just going to add about the conduction. You mentioned it, but I want to kind of reiterate that if you have a very good glass with a very low U value, or a very high R value, either way, the thermal performance of the unit as a whole can be detrimentally reduced by putting in a non-thermally broken frame. A great frame won't make up for poor glass, and a poor frame won't make up for great glass. So really having both is the best way to understand the total performance of a window. And getting the two is difficult because they're coming from different manufacturers, the glass and the frame itself, and finding how it performs in that frame is going to be important, but hard to get at.
That's one of the things we struggle with in energy modeling all the time.
Yeah, it is.
But hopefully, through our analysis, we're able to find that balance point temperature for the building that's optimized for the U value, the R value of the glass that we want. So in terms of light and heat gain, which are one and the same, all of that light is either reflected, absorbed, or transmitted. And the steeper the angle of the light, the more is reflected, and the inverse is true when the light is hitting the glass at a really low angle, like it is in the west and the east in the afternoons and mornings. So taking a standard clear double pane insulated glazing unit, we look at the solar amount of heat transmitted into the space, 70%, or a 0.7 SHGC, and then the visible transmittance of that glass, how much light makes it into the space from the exterior, and that's 0.78. So very high solar heat transmittance and a very high visible transmittance. And looking at the light to solar gain ratio, it's about a 1.1, but we can do better with just some very simple upgrades. Just by tinting the glass using a spectrally selective tint, bringing it down in terms of the visible transmittance, but also adding a low E coating to that number 2 face, that will improve the glass performance tremendously. In fact, taking it to a light to solar gain ratio of about 1.83. And you'll notice that both the solar heat dropped and the visible transmittance dropped, but not in proportion to one another. So we're still allowing a great amount of light in, but less heat. And this is what the DOE sort of targets for spectrally selective glass, anything with an LSG of 1.5 or above.
Yeah.
But
I was just going to jump in and say that, as a function of lumens provided versus heat, daylighting is going to have a very high efficacy compared to electrical lighting, which doesn't deliver nearly as many lumens of visible light with respect to the amount of waste heat that they give off. So that's a nice side effect of daylighting.
Yeah.
Bringing that peak down even more.
But you have to turn off your lights, right?
Yeah.
If you want to take that credit. And that's where those controls come in. Critical part of the puzzle right there.
Definitely. Sorry to interrupt.
No, that's a good point. Thanks for pointing that out. It's certainly not the only thing you can do. There are a lot of potential upgrades to glass. And just like to point out, this is a very basic overview of some of your options. There are people that spend their entire careers perfecting just one of these technologies. So certainly silkscreen can cut down the visible transmittance and also keep a little light out. Suspended interlayers, heat mirror, for example, can reflect a lot more heat. We talked a little bit about the low emissivity coatings. and spectrally selective tints. But then, Scott, you mentioned thermal breaks earlier in the frame, which would help protect against condensation, especially in high humid conditions or super cold conditions. But there's photochromic and electrochromic glass that is an active daylighting strategy, so it dims when there's more daylight available. And it's commercially available. It's still a little bit on the expensive side per square foot, so we don't see it as much, but hoping for that to come down in the future. Here's a great example of how all these strategies came together. This is the Youngberg Anderson office in Milwaukee. It is an existing building, so it's proof that you can make it work even if you don't have control over the orientation of your building. It's pretty small square footage, but a very high LEED rating and 37% savings over 90.1 2004. You can see that the transparency in this case between the meeting rooms, allowing daylight to penetrate deep into the core of the space. There's definitely a higher floor-to-ceiling height. There's no drop ceiling in this, and it was an old dye house, so I think there are 14-foot clear ceilings. So they're bringing the light in very high and also helping it penetrate deeper into the space.
And using light surfaces as well to assist with that.
Mm-hmm. In good, true Scandinavian, tradition. There's a really good example of those light spaces in the core of the building. Here is the exterior of the building. They used automated shading on this eastern facade. So when the light gets low in the sky and starts to transmit deeply into the space, the shades automatically come down. And you can see in the sequence of pictures, as the shades come down, the lights turn on to kind of balance the lighting levels within that space. Since you had an open office, there wasn't anybody to really own those shades, and it really made sense to automate them. And then having these shades work in conjunction with occupancy sensors and the daylight photo sensors, and commissioning them all to fire at the right times and under the right conditions was really, what made it a great space to work in.
Yeah. But you can also see in the progression how the contrast is really cut down as the shades progress.
Mm-hmm.
In the top left, there's direct sunlight, plenty of illumination, but high contrast between the near glazing and the interior spaces where the people are working. And then in the last picture on the bottom right, the shades are fully down, but they're somewhat transparent, so they let enough light through to not have the electric lights turn on completely. So you're saving energy but not turning the lights on all the way, and you have a nice, even foot candle distribution across the working plane.
Yeah, and I love how that the shades are up on the opposite facade there.
Yeah, right.
Because it's all about orientation. So that's how you take advantage of orientation when your building footprint is fixed.
Yeah. One of the worst things that can happen to a daylight design is to be, completely mitigated by the occupants because, they just can't see the computer screen anymore. So the blinds get pulled, and then no one thinks to open them back up when it's, not as glare of a condition outside. And then months pass, and the electric lights stay on, which this design can mitigate that opportunity.
Great.
So what is the maximum height of ceiling where top light begins to become less effective?
That's a really good question.
And if it's something that's a little bit too detailed to answer on the air, we can certainly tackle it.
Right. Well, in general, it's hard to do good top lighting in this cold climate when you have a very low ceiling. We have it in this space, and it's about 10 feet, and it actually works really well.
Yeah.
but there's typically a drop ceiling, and it's a little more expensive. Top lighting works really well in like retail conditions where you start to see that, 12 to 15 foot range. And we've done a number of warehouses, industrial facilities, where it's 25 feet plus to like 35 feet, where it's great. You get a diffuse skylight in there, and you space them correctly. Use a tool like SkyCalc to help you space them, or the manufacturer. They definitely have some great insight into the optimum spacing for their own products, and they can help walk you through that. So, I mean, at above 30, at the higher you go, the greater daylight zone you have as a potential to you. So I've only done buildings up to 35 feet, and it's worked in all of those.
Yeah, really high bay opportunities. As long as you have enough skylight to floor ratio, you can get the light down from that high. I would just be worried if it was the aspect ratio of the building started to become less than kind of 1, where the floor plate was substantially smaller than the building height, and then you start to get a lot of light loss from there. It'd be a great thing to study, though. For a given skylight to floor ratio, what the ceiling height maximum would be.
Yeah, and what I can think of is an atrium of a large corporate headquarters where you have maybe 6 floors and then a skylight. What does the light do? Or like a large retail mall facility where you have a couple of floors. I'm thinking Mall of America.
Yeah.
But that's something that I think would take a very specialized approach and would really push for a simulation to understand the specific dimensions of the space and predict as to what might happen.
Yeah, you can definitely do it. There's daylit atrium out there that are higher than 6. 12 floors, 15 I've seen.
Yeah.
So
definitely becomes more customized the higher you go, though.
Yeah, that's a good point. It's a really good point.
Okay, moving on to a question about skylights.
Sure.
Wondering if you could re-explain the rule of thumb for skylight height.
Sure.
Skylight height? I guess I can assume that means the area over which a skylight can cast its light.
Right, yes. I think you did this earlier in the presentation.
Yeah.
It's just
I think I
a bit of
botched it
review.
earlier. So a single skylight can basically affect a daylight zone that is circular. And the radius of that circle is going to be proportional to the ceiling height, or how far the skylight is from the working plane. And the rule of thumb for that is it's about 1 times. The radius is going to be 1 times the ceiling height of the skylight.
So just as an example, if you have a ceiling height of 20 feet,
Yep.
and what's your daylight zone for just a small skylight? It's 20 feet in both directions, so about 40-foot diameter circle.
Yep.
So that's your rule of thumb for daylit area for skylights. But again,
And that only extends out to the nearest partition. If you have a partition or a set of racks and shelves that are within that area and are approaching the ceiling height, say in your 20-foot example, 10 feet or 15 feet, then it's going to cut off the area out of that, because the light entering from a skylight basically comes out in what can be assumed to be a cone. And we're talking rule of thumbs here, but it's a 45-degree cone down to the floor, and that's how you get that nice circular pattern.
right. And I think, developing a skylight well with highly reflective surfaces and angles to help bounce the light around can definitely diffuse that light. Certainly the selection of the skylight and managing those properties would change that as well.
Yeah.
So,
Great
Okay.
new skylight designs out there.
yeah.
Okay, here's a question about building orientation. when you were referring to the bad and the ugly scenarios.
Oh,
Can
I
you
got this
think
one.
back to that?
Yeah, I can. Sure.
All right. If a building site restricts me to orienting the building between the bad and the ugly scenarios, how can I still effectively incorporate daylighting strategies?
It's a great question. So minimize the amount of view glass on those scenarios if you can. You know, if you can bring in light high, it can be more direct. So a clear story option is great. Skylighting is a great option. We showed automatic blinds in that last example. So, you know, when the sun isn't in the western horizon, you are getting that natural diffuse daylight. So those are 3 ways you can do it, and I could think of a couple more too.
Fins, like in that San Francisco Federal Building that had the same restrictions in the big west facade. You know, they had vision glazing on that, or was it east? The east facade.
Right.
But you know, they used vertical fins,
Right.
so that when the sun rose in the east, the fin extended out from the building and cut off that direct sunlight, and then the occupants weren't forced to draw the blinds and remove the daylight from the space.
Yeah. So that's a really great example of taking a high glare potential and then cutting it. I think the Phoenix Public Library by Will Bruder is a great example of those fins as well. They basically, they catch the light and bounce it into the space, so it's not a direct beam, but it's diffuse. And so making sure the properties of that material, in the San Francisco Federal Building, it was a fritted glass, help reduce that glare.
Translucent blinds, we pointed out in the Engberg-Anderson example.
Right. European buildings, old European buildings with thick walls have that deep shadow box detail, which is also great. You know, those are splayed surfaces that bounce the light around, too.
Yeah, there's a lot of techniques to minimize the glare potential and really bring out a daylight design, even if you are limited by orientation. It's easier if you aren't.
Right.
If you have the right orientation, it just makes your life easier, but you can still do it without it.
You know, the cheapest possible way to do it is just to put in really dark glass.
And 20, 30%.
Yeah, lower than that. I've seen it in the teens.
10%.
And it's a reasonable solution, but it does cut down on the view. So,
It's the trade-off.
That's the trade-off.
Okay. I think we'll do just a couple more.
Please.
Sure.
Are there any daylighting plans that I could use to help with my own daylighting design?
If you use this slide presentation and answer kind of all the conceptual questions, I think that would be a really, really good plan. Certainly, there are some examples on the website in terms of our links.
Is there a daylighting plan linked? We should do that.
I think if you've answered all these questions, all the performance targets, all of the concepts, and then set about a way of predicting the use and then coming back and measuring it, those are all the elements of a really good plan. And that's all you need. It's not rocket science, but
Okay. And we have I think we'll wrap up with a final question here. And
Sure.
of course, the other questions will be forwarded to our instructors for follow-up. Someone wants to know what other courses you might be offering, maybe on more specific concepts that you've addressed today, such as glazing and other.
Well, next week we have the webinar that's tailored more towards the tools and analysis for daylighting. But, glazing is a great example, and the more feedback we can hear about the type of topics that people would like to see, we would love to present more, especially in the fall when, we have a little time to develop a few good topics and get some more information out there to designers and practitioners. Okay.
thanks.
Thank you.